Rohan, are you still there or no? Okay. So we were talking about this, excavation, tunneling in rock. Okay, and then we discussed about, how do we decide whether this wedge that is forming in the underground excavation will slide or fall, and if it is sliding, how to get the factor of safety, and how to calculate the volume of that thing, the weight, and right. So all those stuff. Now today we will be quickly see how this on-wage program works. Okay, so this let's say calculating what is the size of the weight of the wedge, and the factor of safety becomes a little bit difficult when you have a curve kind of boundary geometry. Okay, so what I'm saying is if your excavation geometry is like this and you want to calculate what is the wedge, you can calculate it from the area of this triangle, right, or the volume of the wedge that is forming. But if it is any complex kind of or different shape, then it becomes a little bit time taking. So what of course you can do it manually, but it takes time. So this on-wedge program, like this is a software for same the one we used for our phase 2 thing is called rock science. So I'll quickly tell you how this software works and how to do this the find the factor of safety and do the design of these wedges. So we have these cases here, we have 3 joint sets. Okay, so joint set 1, joint set 2, and joint set 3 in stereographic projection. This looks like this. Can anybody tell me it will slide or fall? This wedge, 3
Sir,
wedges,
it will fall.
it will fall because the center is within that like this intersection area, right? So yeah, we need know that this will fall, and maybe this will form some side uh, in the side it can slide. Okay, so we are going to check those things using this software. This is pretty simple kind of software. I'll quickly show that. Uh, yeah. So in this software, first thing is to make the geometry, right? Like make the tunnel or the excavation. Oops. Just a second. Let's get it here. Okay, so here is the same kind of thing. Like go to opening. You just remember this thing. Okay, this is the one you're going to submit it in your report also. So add opening section. Okay. So now here it will ask you to put the coordinates. So first let's see what are the coordinates. So in here this is our tunnel, let's say. Okay, and let's make this point. This is 0, 0. So what is this point? Can anybody tell me this one here?
So minus 3.5 on.
Minus 3.2, right?
Yes.
Minus 3.5 minus 3.2. Okay, so this is 3.5 and minus 3.2, and this is your 3.5 and 0. We need another point here for the arc. For the arc, we need 3 points. Okay, so this point is 0, 6.7, 3.2. So this is 3.5, right?
Yes, sir.
Okay, 3.5. And this is minus 3.5 and 0. So let's make this thing here. So first point here, you can type it let's start from this corner here. Okay, so this is minus 3.5 comma this minus 3.2. Okay, press enter. Next point is 3.5 comma 3 point, sorry, minus 3.2. Okay. Next point is 3.5 comma 0, 3.5 comma 0. Okay, now we need an arc here. So just type, to get the arc, you just type A is for arc. So it will ask, enter the number of segment in arc. Let's make it 40. Okay, so 40, and then it's asking in the bottom corner, you can see, enter the second arc point. So a second arc point for us is 0, 3.5. 0, 3.5. Okay, and then it says enter the third arc point. So third arc point is minus 3.5, minus 3.5 comma 0. Okay, and this is the last one. So this is our, this the same tunnel. So now once this is done, go to analysis, and project setting is the same kind of thing. You just take some units, and title, you can give it something, and click OK. So let's keep the default unit here. Now again, to analysis, go to input data, and you can start with orientation. So let's trend means with north. Let's say this is the we are looking from the top, and like this is north, and in what direction the tunnel is with the north. So this is north, and let's say this is 46 degree. So the trend is 46 degree, and plunge means with horizontal, how much angle it makes. So this is a tunnel, let's say, with horizontal. What is this theta? So this theta is our plunge. Okay, why we keep some slope is to drain out water. Okay, because if it is horizontal, the water will like stuck there, and it will create problem during construction. So we keep some let's say 5-10 degree angle. So that angle is our plunge. So but in this case, let's say we are keeping those 0 and 0. Plunge is 0, means it is horizontal, and then just keep this default unit weight of rock and water thing here. Okay, now the point is, let's go for this this what is this called, your joint one. Our deep and deep direction, we can take it from here, is 70 plus minus 5 degree deep. So 70, let's keep it 70, and deep direction is 36. Okay, second one is 85, and deep direction is 100, 144, 144, and this is 55, and this is 262. Okay, so if you have more joint sets, you can add it, but then you need to at a time you can combine 3 joint sets. Is this okay? Like, did you, anybody has any question up to here? So you can add more joint sets. Okay, so 4 joint deep and deep direction you can give. You can add 5, 6. So whatever the number of these joint sets that you can insert. But at a time, you joint combinations you can put only 3. Okay. So is this clear? Anybody?
Yes, sir.
Okay. So let's say for our case we have
So
3
sir, we
joint
have to
sets.
use exactly these values.
Yeah, we have to these values, this plus minus thing. I'll give you the range. Okay. So for your case, for your project, you take some random values, starting, like you can start with let's say 40°. This is deep, and this is deep direction, and this is joint. Okay. So this for your project, okay? J1, J2, and J3. You just keep this deep constant at 40. This is 45. And let me see what else I'm taking. Right, okay. Opening input data. Okay, 60 to 80. So let's keep it 60, and this is 260 to 300. So this is 40 to 80°. So this is 160 to 200°. Okay, so you just have to choose any number between 160 to 200. So you can take let's say 162°. Somebody is taking 165°. So any number between these things. So this will be different for different. You just don't copy from your friend. Okay, you just take your own. So take any value between this, any combination, whatever you like. Is this clear?
Yes, sir.
Okay. So for our case, we are taking these values, and that is let's go to this thing again, and then joint properties. So have you given some joint properties here? Okay, so let's take this default value of the joint. Okay, so for your case, just a second. You just choose phi value friction angle of the joint to be between 20 to 40°. Cohesion of the joint between 5 to 10 ton per meter square, and tensile strength equal to 0 ton per meter square, and then waviness equal to 0°. Okay, so this is what you need to choose any value between, let's say, 21°, 23°, or whatever you want. So you take one value from here, 20 to 40°, and C value from 5 to 10, ton per meter. Somebody is taking, let's say, 5.63 or something, whatever value you want, you just put this value. So let's keep this value, put these values here. Okay, and just apply and click OK. So this is it. So this, you are done with this, this on wage analysis. Okay, so there are a few more things you can quickly go through here. Like what are the wages that are forming? Let's see that. Okay, first thing is that. So yeah, you just click this one here. Can you see this?
Yes, sir.
Okay, so you just click this one, and if you double click in this one here, it will show you the same thing. Okay, the same wage. You can just rotate it a little bit if you do whatever you want. So you have basically 6 wages that has formed 1 to 6. 6 is a little bit small and at different location. Let's say the most critical one is 8. Okay, you can see factor of safety is 0 with the parameters we have taken. The weight is 31.31. It's a little bit different than ours. So we need to check why this is happening. Yeah, so let's see. These are the different shapes of this, or maybe this the weight of each wedge and what is the corresponding factor of safety. See, FS is 6.63 633. So this for 7. 7 is this one. So because we have good this friction parameters, then this factor of safety is more. But if we want to reduce the tension value, let's say make it 0, then it will change the factor of safety or this weight 7. So you see the factor of safety reduced to 0.49. Okay. So let's say this is the case. Did you understand? Anybody has any question up to here?
That with this we clicked on 3D wedge view, and after that,
Yeah, you just click this 3D wedge view. Okay, then you can see where are the wedges. You can rotate it and see what are the shapes, right?
sir, did you click somewhere else after that?
Oh yeah, I double click this one. So if it is 3D wedge view, then the top view, side view, front view, all the views will be given. Okay, so if you double click this perspective view, it will look like this, and then you can rotate it and see whatever it is. Okay, if you double click again, it will come to the default view. So if you can take, you just copy these views and one by one and put it in your report. That okay, these are the wedges that are forming. Okay, so if you want to, reduce this waste size and improve the factor of safety, then again, what you need to do is you need to go to input data and then change the orientation of the tunnel. Let's make it 46 degree here. Okay, and when you apply this, maybe the wedges, the size of wedges that were forming, the 8 is the most critical one. This is the size is reduced little bit. Okay, so this is the way you change this, and see in the side you don't have any wedge. Okay, the only wedge you need to take care of is wedge number 8, which is on the roof. Is this clear? So this is how we decide like what should be the orientation of our underground excavation. Like if you are constructing some cavern or whatever it is, or the tunnel. So this is how we orient it from the beginning itself. Yes.
So, sir, we have to change the trend in order to get, I mean, the minimum wedges.
Yeah, minimum wages with like least like most favorable kind of condition. Okay. So during our south site investigation program, first we see that in that location, like what are the wedges, the joint sets. We get those orientation, and then we try to orient the excavation such that our support requirement will be less. Is clear? So
Yes, sir.
let's keep it to 0 degree for now. So in your report, you can do whatever you want. Like maybe you can find out what is the support requirement. Yeah. So and and you can find the ideal orientation of your tunnel. Okay. So let's keep this one. And next thing, what we need to do here is to, because like this wedge roof wedge is having factor of safety 0, we need to support it, right? How to do that? You just click this perimeter support designer. So you just click this one, and this thing will come. And in here, what we need to do is provide this add pattern. Click this add pattern, and it will ask. Okay, so what is the length? What is the spacing? What is out of plane spacing? So for your case, what you can do is, let's say you are talking from class 1 to, let's say, class 5 or 4, whatever it is for your rock class. So from Q classification system, you know what is your length of the rock bolt and what is the spacing of the rock bolt. So you just put those values here, and for different class it will be different. So you can do some different wage analysis. Okay, for different class of rock. Is this clear?
So sir, we will have one class of rock or two, three. It can be more than one. I mean,
It will be more than one, right? Like for your based on your Q range. So you remember that Q chart? Like we divided the whole thing
yes
in
sir.
different class. So you can put this to get what is the length and spacing of this thing. You can do separate wage analysis for different class of rock.
So sir,
Okay.
for all the classes we have to see, and we have to see
Yeah,
which one.
ideally, this is what we do. Okay. It's totally up to you. If you want to give one case as an example for runway analysis, I'm okay with that. But if you want, if you have 4 classes or 5 classes, you can give 5 support design. Because we when we design this tunnel, we don't design it like we cannot say that for wedge analysis this is what we are getting, so provide this support, and from our APM analysis we are getting something else, so provide that support also. We don't do that, right? Like we see that what is the best combination of the support, so that it is supporting, or it is working for both the cases. Okay, so from Q, you just get this value length of this and spacing of the rock bolts, and provide it here. Okay, so let's say the length is 2.5, and keep the in place and out place spacing, 1.5 and 1.5. So you just keep this in plane and out of plane spacing same, and click OK. Then this kind of thing will come. Okay, so you just click anywhere, and you just take your mouse all around. Okay, and click. So this will give us our support system here. And see, now the factor of safety of wedge 8 has been increased from 0 to 1.7. So this support system is working fine for this tunnel. Okay, is this clear?
Yes sir.
So if you want to put shortcut, also add a layer thing is there. Okay, so you just take this default property of shortcut, let's say, or maybe depends upon what what is the for a different class, what is the shortcut thickness you are taking, and you can apply this shortcut. But typically, from when we do wedge analysis, we don't consider in real case, in when you are designing a real tunnel, we don't consider shortcut. And the reason is, how this shortcut works is, let's say this is trying to fail, and the shortcut is somewhere here, and this is trying to shear. Okay, the wedge tries to shear, but it's very difficult, in a big cavern or a tunnel, like whether the shortcut thickness is uniform in that location or not. So it's better not to believe in the shortcut thickness and just rely on your rock bolt. So when we design the tunnel, we don't consider the shortcut, only with this rock bolt, whether it is stable or not, we see. Okay, but if you want, if you are sure for your case that your shortcut thickness is uniform everywhere, then you can consider shortcut. Is this clear? Okay, so if there is some influence of in situ stress also, if you see analysis and field stress, if you put in situ stress, yeah, so it's saying that it all increases, and whether you want to consider in situ stress or not. Just click OK, and then use this in situ stress value. Okay, let's say we are just using this, applying this thing. So it increases the factor of safety. Okay, but let's not use this in situ stress. But if you consider in situ stress, it improves the factor of safety. Okay. So yeah, so this is it. It just please go through these whatever it is written here. Okay, so this most of the thing I have already talked here. So if you do this again, you can go to this analysis here, and you can see what are the which are the support that has been provided to these wedges. Okay, another thing, when you are doing wedge analysis, this has factor of safety of 5.6, and this 2 has factor of safety of 3. So in that case, like I can, what I can do is adjust this space. So I can remove the, this, what is your, the rock bolt in these locations. So I can only provide it in the top one. Okay, just to save some rock bolts. Okay, and click. Okay, so this is again, yeah, this is sliding, and this is factor of safety is 0.49, and 6 is okay, 2 is 0.44. So that means you cannot do that. Okay, so at least you need to provide some support here. Let's say one rock bolt and one rock bolt here. Okay, so and this is good enough to take care of that thing. See, all the rock bolts or the wedges are having factor safety 1.5 or more. So you can play with this to optimize your number of rock bolts, right? Is this clear? Anyone?
Yes, sir.
Okay. Yeah, so then you can just click copy thing and take the information, put it in your report, right? To show, yeah. Okay, so next part of this course today, I will quickly tell you about, this is, like this is when the
Excuse
stresses
me,
are
sir.
less. Yes,
Excuse me, sir. Sir,
yes,
like first we will change the trend in such a way that wedges are minimum,
yes.
and then we will put the rock bolts in such a way that we need minimum rock bolts to support our wedges.
Yeah, support our wedges with factor of safety more than 1.5. Like in this case, this is 1.6. So you are good here.
Sir, also from the phase 2 we will get some configuration for this rock bolt.
Mm-hmm.
So sir, what to choose between the two?
Yeah, like this full phase 2 or this. So what you are going to do is, first you are going to get the support from your Q classification system, right? Then you will check it using this FEM analysis. So if you are okay with the FEM analysis, like that support system, so you can of course choose it from the FEM analysis itself. Okay. So you have a valid question here. The thing is, you can take it from your this FEM analysis. Okay. Is this
Yes, sir.
clear? Okay. Yeah. So now let's move to this stress induced failure and design. I'll quickly go through this. So we talked about, if the stresses are less than the wedges which are forming, that we need to be careful, especially in low cover regions. So these wedges are a big problem. But when the depth of this underground excavation is too high, let's say in more than let's say 500 meter or something. Again, it depends upon the quality of the rock. But let's say in this range, the stress problem becomes, important, and we need to know whether our tunnel boundary is going to fail or not. So fail or not. Just a second, please. I'm getting a call. Yeah, I'm sorry. So, and if any of it is failing, what is the support requirement? So these are special cases when we have this stress-induced failure. Okay, so in here we have two things. One is we will discuss. There are many things actually. We will quickly discuss two things. One is falling, and second one is squeezing. Okay, so yeah, so let's see them one by one. So spalling means like what happens when we excavate something. Let's say space, simple circular case. So if the stresses are high enough, what happens? The boundary here like fails like this, and see the slabs. Even in the intact rock, some slabs they try to come out. Okay, so this is called falling. Okay, this is clear. What is this falling? And this before this, in this case, the boundary was very much circular, but this thing, this corner kind of thing, that it tries to come out in the rock. Even if there is no joint, it is intact rock. This try to fail like this. Did you understand this?
So can you repeat it once?
Yeah. See in this case. This is actually mined by tunnel. So this is a horizontal tunnel which was circular in before. So this is from URL, Underground Research Laboratory in Canada. I was fortunate to involve in this project. So this is a circular horizontal tunnel. Horizontal tunnel. So like when the circular part was excavated, this is very much intact rock, very good quality intact rock of black dubonate granite. It's called LDV granite. So, but like when this tunnel was excavated, it formed something called notch. Okay, so this part of the tunnel and this part here that failed. Okay, because of high in situ stress. And like even you can see this stresses here is so high that like there was some this is called spalling failure that happened in here. Okay, and see, because this is sigma 1 is a little bit oriented in this direction. This is sigma 1, so it is parallel, like where this sigma 1 and uh, or maybe you can see it is perpendicular to your sigma 1 direction. So this is where this falling that occurred. Okay, so how do we know this, whether the spalling will occur or not, is, given by something called crack initiation stress. This crack initiation stress. So what does this mean is, if you remember your UCS test, this core from the same rock when tested in UCS, this same rock here in this URL in Canada, like this is same rock we have tested in laboratory, and this is the stress strain curve for that Lac-du-Bonnet granite. Okay, so it has some initial nonlinear behavior that we typically see, and the sample failed at around 220 MPa. Okay, and then when the stresses here was analyzed using FEM analysis, we found out that this crack initiation, this falling occurred around 110 MPa stress. Falling at 110 MPa stress. And if you compare this thing, so this curve here, the UCS of the rock is 220 MPa, but around mid of this, around 50% of this, UCS, the tunnel started, the spalling started in the tunnel. Okay, so at 110 MPa, then we then it was further investigated, and there is a term which is called crack initiation stress. So what happens when we load the UCS sample? The crack forms in the sample way before this peak. Okay, it's not like like when the sample reaches 220 MPa, the failure will begin. So the crack actually initiates around 0.45 times UCS value. So this is the magnitude at which the crack actually begins in the sample. And that location here, which is around 0.45 times your UCS, is called crack initiation stress sigma Ci. Okay, so there are ways how can you calculate this crack initiation stress. We are not going to discuss about this thing here. You just remember this crack initiation stress is 0.45 times your UCS. So when you are doing any kind of design, so if at any location around your boundary of this tunnel, let's say sigma boundary at any random point, right? So sigma boundary is greater than 0.45 times your UCS of that rock, then spalling occurs. Okay, so this is what this is given by Nixer and Martin. So this is what says that this is for different type of rock. They compiled they plotted UCS versus your crack initiation stress sigma Ci, and they found out that for most of the rock it is around 0.45 times your UCS. Okay, so as I said, if you are doing or designing any tunnel, if you in the boundary you found out that the stress value is greater than 0.45 times your UCS, then you can expect some spalling there. Now, second thing is what is the depth of the spalling? Is, let's say if A is the radius of this tunnel and DF is the radius of this spalling, then you can for different cases they have plotted this DF versus A. Okay, for sigma max versus UCS. So if you know your sigma max, right, and let's say this at the boundary here, your sigma max is, let's say, 155 MPa. Okay, and UCS, this is, let's say, sigma max. And UCS of the rock is, let's say, 220 MPa. Then this divided by this becomes, what is this 155 divided by 220? Can anybody quickly tell me?
Sir, 0.7.
Okay, so 0.7. So 0.7 is somewhere here, right? So you just draw a vertical line here. Okay, and you can find out that the ratio between for in this case here, the ratio df by a equal to 1.4. Okay, so if this is 1.4, you can calculate what is your df. Df equal to 1.4 times a, and if you subtract df minus df minus a, that will give you the depth of this failure zone, right? Equal to depth of failure zone. Is this clear to everyone?
Yes, sir.
Okay, so this 0.4 times a. So this is how you find out this depth here, and if it is falling in your
Sir, is it 0.4A or 1.4A?
no, if you subtract 1.4 minus a is 0.4a, right? So df is 1.4a, so df minus a is 0.4a.
Oh, got it, sir.
So what I'm saying is here, because you found out that okay, you are designing a tunnel and you found out that the stresses are maximum here. You know your this height now 0.4a. Then you can provide the support system, design the support system accordingly. Okay, that so that it can take care of the load, or maybe you put some wire mesh here and put some stick with some rock board. Okay, design accordingly. This is like the way we did it before for the wedge analysis. Is this clear?
Yes, sir.
Okay. So typically it's difficult to capture this difficult to capture this spalling using FEM. Why is, like we are saying that the stresses are less than UCS, still the rock is failing here. So the UCS, how the FEM works, it's not going to capture this falling. Okay, so for this, you need to do some cohesion weakening, frictional strengthening model. So just if you are more interested in this modeling kind of thing, you can just do this CWFS to get the failure zone or the spalling zone for using FEM analysis. Okay, so you need to change in the code somehow so that it will capture this behavior. Is this clear?
Yes, sir.
I don't know. Okay, no worries. Just let me know if you have any question. So in spalling, you just quickly go through this. Like we provide, this is something called this wire mesh. Wire mesh, and then we provide the steel ribs also, right? To take that load that is been falling. Because what happens once this falling occurs, is not going to stop. Okay, once it will go on and on, right? So if you can stop in between, then it will not propagate. So in right time you need to stop the falling. Okay, so this is how they have supported this thing. Second part, as I'm saying, is called squeezing. And as noted by Einstein, this is Herbert Einstein, or not Albert Einstein. It's from MIT. So he works in this squeezing rock. So as noted by Herbert Einstein, squeezing is a time-dependent shearing of ground leading to inward movement of the tunnel perimeter. So what does this mean is, like before we saw that, after 2D, if the tunnel is excavated here and this is more than 2D, the deformation almost stops. Okay, but that is, as we have talked once, if the convergence is less than 1%. So in that case, the deformation will stop. But if it is more than 1%, it never stops. It keep on increasing. Okay, the tunnel will, the failure zone will keep on growing, and the tunnel will come inside. Okay, continuously during your, excavation of the tunnel. So it's kind of crazy condition when the stresses are, too high. I will show you some figure here. See, maybe the tunnel is progressing from here to here. Okay, and this because the material is weak, this is getting converged. Maybe this is more than 1 meter. Okay, so yeah, this is 10-meter span tunnel. So this is called your squeezing condition. I'm sorry, I'm going to take 1 or 2 minutes more to finish this off. Okay, so this plot here says the convergence in mm. So these are the target points in the boundary of the tunnel. So how it is moving? So that is plotted here. Okay, so in maybe in 10 days the movement is only 30 mm, but it is keep on increasing, like for the red case here, right? And up to, they have monitored up to 1,000 days. So it's going on up to 100 years, and again it depends like with what is your case. So maybe for your case this will keep on increasing. Okay, so this is called squeezing condition. And anybody has any doubt here or any question? Okay, so yeah. So now how do you know that? Using this figure here. So this is the last concept that we are going to discuss. So see, there are two things here. The tunnel convergence divided by the diameter of the tunnel. So if this is the diameter of the tunnel and delta is like the convergence. Okay, so if the tunnel is and you divide this tunnel convergence with by your diameter and multiply with 100, if that becomes less than 1%, few support required. But if the strain or this value greater than 2.5 to 5%, you know, like the severe squeezing problem that occurs. So that is why I asked you, if the tunnel deformation is less than 1%, you just say that, you know, this is our safe condition for your project. Okay. So, yeah, so what it is saying is, you know, like if you know your rock mass strength, sigma cm, and the maximum principal stress, especially in case of circular tunnel. Okay, so you are constructing a circular tunnel, and you know that this is sigma 1 and this sigma 3 direction is here. And if you know what is the UCS, so this sigma cm is your UCS of the rock. So if you know your UCS, you know your sigma 1, then you can calculate what is the, you know, that value. So if it is, let's say 0.1, okay, so the convergence, you can calculate from here what is this value. The tunnel convergence you can calculate, and if the tunnel convergence is this much, you can see that, you know, like you can get different kind of values. Is this clear? So maybe if I give you the exam, like let's say my sigma 1 is this much, UCS of the rock is this much, you should be able to predict what will be your tunnel convergence. Okay, and able to see whether what kind of squeezing condition you will expect, extreme squeezing or very severe squeezing or severe squeezing. So you can get it. Is this clear?
Yes, sir.
Yeah. So yeah, please go through this figure. So then what kind of support system we need is, you know, like we have different support design for this kind of excavation cases. This is L, S, C yielding element, especially the yielding element. What it does is, you know, like when we put it in the boundary of the tunnel, right, with a shortcut, and so that, you know, when the tunnel converges, this rigid support, it allows some kind of deformation. Okay, so in this case, these guys, like these are some spring type of thing, you can say spring kind of behavior. Okay, so when this tunnel squeezes, it can take that deformation. So we have to put different rows of this thing. Okay, and we need some special design in this case. Okay, so what is the maximum deformation we are expecting? What is the capacity of each of these yielding element here? Okay, so or maybe we need to put some spring kind of, you know, this kind of support around the boundary. Okay, so this has been put in the Alps in Switzerland, like those kind of, you know, or this Wakembu Quiber tunnel. Okay, so if you want to know more about this support system or this kind of, you know, sliding gap, so that main thing is when you are supporting the tunnel, this tunnel, the tunnel boundary, when it is squeezing, this also the support system will also deform along with that. If it is too rigid, it will you know, break this support system here. So you need to allow the deformation to occur. So and finally this whole thing will stabilize, and this will take the or maybe apply the required support pressure, and the whole thing will be stable. Okay, so this very good example is the Switzerland Alps example. So if you want, you know, you just can Google this Kovari et al. 2005 paper. Okay, so yeah, these are the support systems. This is how it is being applied. Okay, so this is the tunnel is called Gotthard based on it. And you can see the tunnel depth is around 2.4 kilometer below the ground surface. Okay, so huge amount of stresses, and they had some squeezing problem. Okay, so let's stop this thing here. So our exam questions will be up to here. Okay, and as I said, I'm going to share something with you. Okay, let me show this thing. Okay, courses and okay. So what I'm going to share is this thing here. So this is ISRM lecture series. So I have taken this PDF from there, and this professor is Eric Everhart. He's from UBC in Canada. So you can quickly go through this thing. Like this is about how do we excavate this tunnel. So first thing is drilling and blasting, or we can go for mechanical excavation. So it talks about that, like before. Please go through. I wish we had time, like we had limited, kind of time here in this semester. So you please go through this. It's just kind of, and if you have any question, please ask me. Okay, but this is not exam point of view. Okay, so this is what it is done. Like these are drilling cycle. So it starts with the drilling, right, and charging, blasting, scooping, scaling, bolting, and then surveying. So this whole thing repeats. Okay, in a blasting cycle, and these are the equipment to do the drilling thing, right? And these are the drill bits. So please go through this. What are the drilling patterns you have, like burn cut, wedge cut, and those kind of things. Uh, so yeah. So what is this burn cut? So what is this delay? Okay. So this is how it is blasted to get a smooth, profile like this. Yeah. So we have something called pre-splitting. If we want to less damage to the, this surrounding rock. Yeah, then we have different kind of explosive that we use. N4 and different kind of dynamites and slurry based, emulsion based. So these are different kind of explosive. Please quickly go through this and how these explosive are put. Right, few of you must have gone through these kind of things. So this blasting thing. So you please go through this, right? And also this mechanical excavation, what are the different mechanical excavation machines that we use, like the road header in the left side here. This is called a TBM, tunnel boring machine, right? So how it works, right? This is the part of the road header. Okay, this is a big TBM. So yeah, if possible, I will share some videos also how these things work. Okay, so we have these kind of machines to do the excavations. Okay, so
Sir,
I yes.
sir, I have a doubt regarding that phase 2 evaluation, sir.
Yes, you please let me finish this one and then you can ask. Okay, so this is the one, and then what I'm saying is we had three chapters which are design of caverns, design of shaft, and this instrumentation. So I'll share some notes with you. Okay, just.
So you are muted.
Okay, so that's it. I'm going to share this thing with you, and next week will be our, this Viva. So can anybody tell me like what will be your preferred time in the afternoon?